Welcome to limit of a sequence. Today we will discuss about how to find the limit of a sequence. What is its definition and what is its properties. Mainly we will prove that limit of a sequence is unique whenever it is existing. And we will discuss some of the equivalence condition for existence of limit of a sequence. So first of all the definition 3.1.3 definition. A sequence xn in R is said to converge is said to converge to a point x belongs to R, or x is said to be a limit of xn, a limit of xn if for every epsilon greater than 0 there exists a natural number a natural number k of epsilon such that for all n greater than this k epsilon the terms can put greater than or equal to k epsilon the terms xn satisfy mod xn minus x is less than epsilon. So this is the definition of convergence of a sequence. Let us examine what's the meaning of this. So to explain this, we can have two sequences here. First, I am making the sequences as the sequence is some y equal to yn. Now this means putting the sequence as this 1, 2, 3, 4, 5, 6, 6, 6, 6, extra, 6, extra. It's a sequence, right? Next I am putting another sequence z equal to zn. This sequence is 1, 1, 1, 1, 1, extra, right? Another sequence I am putting is some y dash equal to yn dash, which is going to be as 1, 2, 3, 4, 5, 6, etc. These all are sequences, right? So even if you want to put even numbers or odd numbers, you can take in that fashion. So renaming this, so taking 2, 4, 5 6 sorry, no, 5 will come, right? So 2 4 6 8 10 etc. So I have considered here three sequences, right? Let us examine which and all will converge. Now going back to the definition, what it says, a sequence xn in R is said to converge to a point x, or x is said to be a limit of xn if for every epsilon greater than 0 there exists a natural number k epsilon such that for all n greater than or equal to k epsilon the xn satisfy mod xn minus x is less than epsilon. You have studied about the definition of continuity and all. So epsilon means it's a very small positive quantity, that is a quantity very close to our value 0. Now we consider this sequence. At first you consider z. Now what's the speciality of that sequence? It is a constant sequence, right? 1 1 1 1 1, and we know that this sequence will converge to 1, right? Everything is 1, so it may converges to 1. Let us examine will it converges to 1. Suppose it will converges means what we want to do? We want to have modulus of xn. The term is xn. The sequence term is xn. Modulus of xn minus x should be less than epsilon for every n greater than or equal to some natural number, right? And name as k. So will it be possible here? Here xn means every xn is 1. So I am having 1 minus, suppose I am taking this to be as converging to 1 means 1 minus 1 I will take. Okay, so now this 1 minus 1 is 0, we know that. Now this value is less than epsilon. So evidently this sequence will converges to 1. Now suppose I am taking x as 2 means what will happen? This value is 1. So any epsilon, so if I am taking an epsilon 0.001, I will get this value is greater than 1 minus 2, modulus of 1 minus 2, 1. So this is not possible, right? So this sequence evidently converges to 1. Thus, a constant sequence converges to the same constant in the set of real numbers. Okay. Now, if you are taking this sequence, what will happen? This sequence means here xn is x1 is 1, right? x2, x3, x4, xy, x6. Now this is my x6, right? x6 is this. This is x7, x8. So after this, everything is 6. So there's a possibility that it may converges to 6. Let us see. So what we want to do? We want to check for every epsilon greater than 0. So first you put some epsilon. So suppose I am taking the epsilon value. Suppose I am taking my epsilon value as before 0.001. For every epsilon, it should be true, right? Now we calculate modulus of x1 minus, I'm putting this as 6. Okay, let us see. And modulus of x2 minus 6, modulus of x3 minus 6, etc. Modulus of x6 minus 6, modulus of x7 minus 6, etc. Calculate. Now if you are calculating like this means this evidently you will get x1, right? So 1 minus 6 you will get it as 5. This you will get it as 4. this you get it as 3. This you will get it as x6. x6 is 6 itself. So this is 0. So this is 0. This is everything is after this stage, everything is 0. Now what is that stage? Sixth one, right? From putting from here means after this, when I am finding modulus of x1 or xn minus 6, I am getting everything as 0. Or we can say that that quantity is less than my this epsilon value. So this sequence will converges to 6. That means what this definition says is that after a particular stage, our terms of the sequence and limit of the sequence is very close to each other. Is it clear? Is the idea is clear? What it means is that suppose you have got lot of this is your set of real numbers and you have got lots of points in your sequences, right? Suppose these all are the sequences. So lot of terms should be there. Suppose here also some terms are there. Okay, now here plenty of terms. Now your sequence, this sequence will converges. It cannot converge to a point somewhere here, right? It cannot converge to a point somewhere here. It can converge only to a point over here. Because what's the reason? Because after a particular stage, what is the stage here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, some 11 or 12 I am taking. Now after this stage, what I am getting is loads of points. That means infinite number of points are very close to my this limit x. So after a particular stage, every point of my sequence are very close to the limit of that sequence. If such a point is existing means we will say that that is the limit of the sequence. Now how to say that after a particular stage and all? That means there exists a natural number. See, there exists a natural number. Here I have got it as 12. After this, what will happen? For every n greater than 12, the distance between my points in the sequence and limit of the sequence is less than epsilon. Can I say like that? So after a particular stage, now we are going for the generalization. So after a particular stage means we are putting some k and this is k. So after a particular stage or after a particular natural number, all our xn is very close to a point x means we will say that this x is going to be the limit. Now see in example 3, this was set of even numbers, right? So you take any number, any real number and take the difference between these. It is not very close, right? Suppose you are assuming that this may converges to any real number. That is some real number. I am putting a small r. Now distance between 2 and this r. There should be some distance, right? So distance between 4 and r. Distance between 6 and r. Distance between 8 and r. Distance between 10 and r. Suppose we are continuing like this. We cannot wind it up as after a particular stage, the distance between this r and this term of the sequence is less than some epsilon or which is very close to r. Any number in this sequence is very close to r. After a particular stage, all the terms of the sequence are very close to r. Such a condition we cannot deduct from this, right? So this sequence cannot converge, or we will say that this sequence converges to, this sequence diverges. Now going back to definition, a sequence xn in R is said to converge to a point x belongs to R, or x is said to be a limit of xn if I have said that for every epsilon greater than 0 there should exist a natural number. This guarantees that if you take an epsilon greater than 0, there exists a particular stage. After the stage, every member of our sequence is very close to the number x. Hope you understood the definition. Next, if a sequence has a limit, we say that the sequence is converges. The sequence is convergent. If it has no limit, we say that the sequence is divergent. So convergent sequences and divergent sequences. Converging sequences means it should have a limit. Diverging means it cannot have a limit. As a note, we can see that in the definition I have mentioned there exists a particular natural number. I have taken as, instead of taking k, I have taken k of epsilon. So what's the meaning of that? The meaning is that this natural number is depending on the epsilon value. So if I am taking an epsilon value here, it may have an effect on after which stage my terms of the sequence are very close to the number x. So I have said that epsilon is a positive quantity, right? Suppose I am taking this epsilon as 1. Suppose I am taking this epsilon as 1, means in this sequence, this epsilon value is 1, means I can take from here onwards, from this stage, that is x5 onwards. Now if I am taking epsilon is 2, means I can take from this stage onwards, like that. This epsilon, k value depends on epsilon. That's why we are writing k of epsilon. In the above definition, k of epsilon is used to emphasize that the choice of k depends on the value of epsilon. But in generally we will denote k of epsilon as k by taking in mind that it depends on epsilon, right? This is the knot 1. Second knot. When a sequence has a limit x, we use the notation for denoting its limit is x as limit x equal to x. This is one way of notation, or limit of the sequence xn is equal to x. And symbolically, we will represent as xn converges to x, or which means xn converges or xn approaches the number x, approaches the number x as n tends to infinity. That is, when you're going larger and larger natural number values, our terms of the sequence are very close to a value x, means we will say that the sequence converges to x. Now we will prove that if such a limit is existing, the limit is unique. So here is 3.1.4. We will say that uniqueness of limit. Uniqueness of limit. Theorem. A sequence in R, can have at most one limit. What's the meaning of this? Meaning is, suppose you have got a sequence xn and that converges to some x1, and suppose again this sequence converges to some x2. Okay, a sequence which converges to x1 and sequence which converges to x2, then this will implies that our x1 is equal to x2. So this is the meaning. That means if a sequence converges, means it should have only one limit. So how to prove it? Proof is very simple. First of all we will assume that this sequence has got two limits, and we will prove these two limits are going to be equal. So consider a sequence xn which converges to some points, right? I'm taking as x dash and x double dash. Then xn converges to x dash. By definition, we get, what we get using definition, we get for every or each epsilon greater than 0, we get for every epsilon greater than 0, there exists some k dash natural number, right, such that what should be our condition? Modulus of xn minus this x dash is less than epsilon for all n greater than or equal to k dash. And also, right, this is one condition. Now we are calling this condition as 1. Also, what is given? Our sequence xn converges to x double dash, right? So in the same fashion, for every, which implies for every epsilon greater than 0, there exists, I'm taking as k double dash, belongs to natural number such that modulus of xn minus x double dash is again less than epsilon for all n greater or equal to k double dash. Call this as equation 2. Now what I want to do? Now consider modulus of x dash modulus of x dash minus x double dash. That is, we are finding distance between x dash and x double dash. Now this value is same as, I can have some xn, right? Or else I will write it as x dash, I'm putting minus xn plus xn minus x double dash. Doesn't change, right? Now I can use triangle inequality here. So this is less than or equal to modulus of x dash minus xn plus modulus of xn minus x double dash. Am I right? X dash minus xn plus xn minus x double dash. Call this as equation 3. Now what we want to take? Let my k is equal to, taking this as maximum of k dash and k double dash. Then what will happen? Then modulus of x dash minus x double dash, I have got this as less than or equal to this, right? So this value is less than or equal to modulus of xn minus x dash plus modulus of xn minus x double dash. Now this value is less than epsilon plus epsilon for every n greater than or equal to k, right? Maximum of these two. From where you got this two? From 1 and 2. Does 1 and 2? 1 was xn minus x dash is less than epsilon for all n greater than or equal to k dash. I have taken as k instead of k dash. I have taken as k. That's maximum of k dash and k double dash. So similarly here also for k is greater than k double dash also. So for that also this is true. Now what I got is to be as 2 epsilon I will get. So x dash minus x double dash is less than 2 epsilon. Right. From that can you conclude that x dash minus x double dash is 0? It's possible because we have studied that if a modulus of any value is less than some epsilon, then that value will converge to, or that value is 0, right? So mod of a is less than or equal to epsilon for every epsilon, then a is equal to 0. We have studied that. So, but here we are having 2 epsilon. So to make this as epsilon, we can do one thing here. Instead of taking here for every epsilon, I can put this as for epsilon by 2. Here also I can have epsilon by 2. So what I will get here, these two values is less than epsilon by 2 plus epsilon by 2. So that's equal to epsilon. Now we can use that theorem that modulus of any real number is less than epsilon, then that real number is nothing but 0, right? Since epsilon greater than 0 is arbitrary, a positive number, arbitrary positive number, we get modulus of x dash minus x double dash equal to 0. So modulus of a quantity is equal to 0, which implies x dash minus x double dash equal to 0, or which implies your x dash equal to x double dash. That is, limit of the sequence is unique. Okay, that is limit of xn is sequence xn is unique. So we have proved that. Next we are having the equivalence condition. 3.1.5 theorem. Let x equal to xn, x equal to xn be a sequence of real numbers and let x belongs to R, then the following statements are equivalent. First statement is x converges, that is sequence x converges to small x. B, for every epsilon greater than 0, there exists a natural number k such that for all n greater than or equal to k, the terms xn satisfy mod xn minus x is less than epsilon, and C, for every epsilon greater than 0 there exists a natural number k such that for all n greater than or equal to k, the terms xn satisfy x minus epsilon less than xn less than x plus epsilon, and D for every epsilon neighborhood V epsilon of x there exists a natural number k such that for all n greater than or equal to k, the terms xn belongs to V epsilon of x, that is the epsilon neighborhood of x. So these are the equivalence conditions. So we want to prove these conditions. 4 conditions are going to be equivalent. That is, A implies B, B implies C, C implies D, and again D implies A. So how to prove it? From a close examination of these two conditions, we can easily deduct that A and B are nothing follows from the definition of convergence of limit. So X converges means this is exactly the definition of convergence, right? So A implies B is very easy. Proof: A implies B. It follows from the definition of convergence of a sequence. Now we want to prove B implies C. So assume condition B. Then for every epsilon greater than 0, there exists a natural number k such that for all n greater than or equal to this k, xn satisfy mod xn minus x is less than epsilon. Then by definition mod xn minus x is less than epsilon implies modulus of mod a is less than b. That means minus b less than a less than b, which implies minus epsilon less than xn minus x less than epsilon. That is, here we are having x minus epsilon less than xn less than x plus epsilon, right? So this is exactly they have asked. Now we want to prove C implies D. Now C implies D. Assume condition C. Assume C. That is, for epsilon greater than 0, there exists some k belongs to n such that k belongs to n such that for all n greater than or equal to k, xn will satisfy x minus epsilon less than xn less than x plus epsilon, right? Which implies minus epsilon less than xn minus x less than epsilon. Or this implies modulus of xn minus x is less than epsilon. This means distance between xn and x is less than epsilon. That means when you are taking an x and an epsilon radius ball here, an open set, then your xn will be somewhere here, right? So this implies this xn belongs to epsilon neighborhood of x. So which implies your xn belongs to epsilon neighborhood of x. So we have proved that one. Now the last one is D implies A. D implies A. Now suppose D. Now suppose your condition D. That is, for epsilon greater than 0, there exists some k belongs to n such that xn belongs to v epsilon of x for n greater than or equal to k. So this implies modulus of xn minus x is less than epsilon for n greater than or equal to k. Okay, so which implies that is, for epsilon greater than 0, there exists k belongs to n such that modulus of xn minus x is less than epsilon for n greater than this k. So this implies nothing but the sequence xn converges to x. So this is a proof, very simple one. Exactly, we can make this proof in a single line also, because whenever modulus of xn minus x is less than epsilon, the meaning is that minus epsilon less than x, xn minus x less than epsilon. Now taking x on both sides, we will get x minus epsilon less than xn less than x plus epsilon. From this, and by definition of neighborhood, we can easily deduce this. Okay, so hope you understood today's class. So any problem, let me know. So I am winding up today's session here. So today we have discussed about limit of a sequence First we have discussed what's the definition, then its meaning, then limit of a sequence is unique, and the equivalence condition for limit of a sequence, or the existence of limit of a sequence. Okay, with this I am winding up here. Thank you for your patient listening. Thank you.